Hi everyone, welcome to Mostly Math. Today we'll be talking about the fractional Schrodinger equation, which looks like this. H bar d psi of r and t by dt is equal to some fractional Hamiltonian h alpha times psi, where the fractional Hamiltonian is just some coefficient. It's just some coefficient d alpha times, very interestingly, minus h bar squared Laplacian to the alpha over 2 power times psi plus some potential times psi as well. Now, where does this equation come from? What do you mean by fractional derivatives? Okay, let's back up a step. Sure, we can do that. So the ordinary Schrodinger equation, okay, this is the fractional Schrodinger equation. Just the normal Schrodinger equation looks like this. You know, we have IH bar d psi by dt is equal to the normal h psi, which is just minus h bar squared over 2m Laplacian of psi plus v psi. So if you notice, all the difference between the two equations is we have a fractional derivative. So what this means is we can now consider things like d half by dx to the half of some function. We can apply this to functions of x, such as square root of x, and etc., etc. And there are so many other videos that talk about this. Maybe I'll do one in the future. But all you have to know is that you can do fractional powers. Pretty cool. And we basically want to, right. So first I should tell you where the momentum is defined to be minus IH bar gradient, of course. And so the p squared operator is just minus h bar squared Laplacian squared. That's where everything comes from. Not that scary. Just have a new coefficient and some fractional terms. Okay, so we're doing the regular separation of variables on this to solve it, actually. So we're going to use separation of variable ansatz of psi of r and t is going to be, we're going to guess the solution, e to the minus I et over h bar times some phi of r. So basically what we've done is we've separated the variables and already solved the time one to be just the ordinary time phase from regular quantum mechanics, and we're going to hope that it gives us a simple solution. Yep, let's try it out. By taking derivatives, so we have d psi by dt is just going to be minus minus IE over h bar times the function itself. And we're going to have the space derivatives, minus h bar squared Laplacian squared to the alpha over 2 power, acting on psi to be the time phase, times this derivative acting on the space component. So when we put this into the Schrodinger equation, it's going to tell us that IH bar minus IE over h bar e to the minus IET over h bar times phi is just equal to h psi. So we're going to have d alpha minus h bar squared Laplacian to the alpha over 2 power plus the potential acting on e to the minus IET over h bar phi. And since the exponential function is never equal to 0, we can just simply go ahead and divide it. Excellent. We're also going to simplify this here. We're going to put the I down here. So the IH bar is going to cancel with the IH bar to obtain that E phi of R is just equal to RH alpha phi. This is known as the time-independent fractional Schrodinger equation. Not sure where the fractional goes. Fractional time-independent Schrodinger equation. And it is the equation that, in general, we would like to solve given a potential V of R. In this video, we're not going to solve it exactly. We are going to make an approximation, but you'll see, it'll be pretty cool. Pretty cool. We're actually going to generalize the oscillator, the harmonic oscillator from quantum mechanics, and we're going to find the approximate eigenvalues for it. And we're also going to show that as our alpha goes to 2, so we get a quadratic potential, our fractional oscillator will have the same eigenvalues. So just for reference, we're going to be writing down this equation up here. So we have E phi of r is equal to our Hamiltonian, and we're going to be talking about a potential V of r to be q squared x to the beta. So as beta goes to 2, this will look more like our harmonic oscillator potential of 1/2 m omega squared x squared. This is just a slight generalization of this. Yep, we're going to let this be our potential here. We're going to write down our equation. So E phi is equal to the Hamiltonian acting on phi. Hamiltonian is Hamiltonian. Gotta get this right. D alpha 2 minus h bar squared, gradient squared to the alpha over 2, plus our potential q squared x to the beta acting on phi. Okay, here's what we're going to do. We're going to use the Bohr-Sommerfeld approximation, or basically old quantum theory, to find the approximate eigenvalues. So in this approximation, we're going to say wave functions don't exist. We don't really know anything about the quantum mechanical wave functions, so we're just going to get rid of them. We're going to get rid of the wave functions. We don't need them. Do not need them at all. I mean, it will be nice to have them, but I just want the eigenvalues. So right now, I don't need them. Okay, second thing we're going to do, we're going to recognize that this operator comes from the momentum. We talked about how p squared is the same thing as this operator. So instead of putting it in differential form, we're just going to put it back into the p form. So, no. P squared was this, sorry. P squared was this. So if we do p squared to the alpha over 2 power, it's just going to be minus h bar squared, the gradient to the alpha power, whatever that means, and we're good. So this is just p to the alpha. And now we're going to treat p as if it's a variable. It's no longer an operator. Yep, E is the alpha p alpha. Yep, this is excellent. Now we're going to treat p as if it's a variable and solve for it, because in this approximation scheme, we want to find the classical turning points of the system, basically where it stops. Okay, so from this, we can then immediately show that p is just going to be 1 over d alpha e minus q squared x to the beta to the 1 over alpha power. Not hard to derive. We'll just be taking q squared x to the beta over here, dividing by 1 over d alpha, and then take everything to the 1 over alpha power. No problem. So these are our classical turning points. Well, rather, this is the momentum. And the turning points is where the momentum is 0, and this just corresponds to E minus q squared x to the beta, which tells us that x, which we're going to be calling xm for x maximum, the maximum x that the system can do, is just going to be pretty simple. Yep, E over q squared to the 1 over beta. See, we just took, yeah, you see what we did. It's fine. E over q squared 1 to the beta. Okay, and just because we're going to be doing some integrals later, let's just go ahead and note a few things about this. Yeah, we're going to be noting the fact that we can rearrange this equation to tell us that q squared over e xm to the beta is 1, and xm e to the 1 over alpha is just e to the 1 over alpha plus e to the 1 over beta over q to the 2 over beta. Keep those in mind for later. We're going to be doing some integrals, and we'll need these formulae. All right, so the Bohr-Sommerfeld, quantization rule instructs us to set 2 pi h bar n plus 1/2 equal to the integral of p over a closed circuit dx. And let's see what we can do about this. Okay, turning points. So we have our potential here. This is V. It's going to be some x maximum that the particle doesn't go beyond. And first, it's going to start at 0. It's going to go over to x maximum. It's going to return to 0. Then it's going to go over to minus x maximum and then return to 0. This is what we mean by one period of the system. So the integral in question is just 4 times the integral from 0 to x maximum of p dx. Fantastic. Just have to use our expression for p and integrate it now. It's starting to look better, All right. So this tells us that the thing we seek is just going to be equal to 4 over d alpha to the 1 over alpha power integral of 0 to xm dx over e minus, not e squared, e minus q squared x to the beta, excuse me, to the 1 over alpha power. Okay. Fantastic. Now we want to do some substitutions, just like we always do. Now we're going to let y to be equal to x over x max, so that y now goes from 0 to 1. And this tells us that, of course, x is equal to xm y, dx is equal to xm dy, and we can go ahead and plop those into our integral here. The integral in question, I'll be evaluating 0 to xm dx e minus q squared x to the beta 1 over alpha power is just going to be, you know what, sorry, I don't have quite enough room to do this. Keep these expressions in your mind, or you can write them down. I just don't have enough room, sorry. Okay. So there's going to be a lot of constants here. Really, you don't have to worry about them if you don't want to. Basically, I just want to show you how this leads to some cool integrals that we can evaluate in terms of special functions. It is confusing, which is why I have to follow my notes here. Otherwise, I'll get all the constants wrong. All right. So we are evaluating this integral, 0 to xm dx e minus q squared x to the beta to the 1 over alpha power. And just to recall, we had dx is equal to xm dy before, and the limits are being changed from 0 to 1. So this becomes xm dy e minus q squared xm y to the beta power 1 over alpha power. And now we want to go ahead and take the xm out because we can. We want to factor out the e to use our relation that we talked about earlier. So this just becomes xm integral dy of e1 minus q squared xm to the beta over e y to the beta. This is to the 1 over alpha power. We talked about this earlier. And we're going to be taking out the e to the 1 over alpha, integral 0 to 1 dy. And now we have, this just simplifies immediately actually. Yep, this just becomes 1 minus y to the beta to the 1 over alpha power. Since these constants together are just 1. It's the definition of xm basically. They're just 1. Okay, now we have this integral. And it's starting to look like something that we can evaluate. We already noted what this combination of constants was earlier. I'm not going to write it for the next step. You can feel free to keep track of it in your mind. So now we'll be evaluating this integral without the constants. So we'll be talking about 0 to 1 dy, 1 minus y to the beta to the 1 over alpha power. We're going to be doing another substitution. Surprise, surprise. We're going to let z equals y to the beta such that y is z to the 1 over beta. And the limits are unchanged, of course. Now we have dy is 1 over beta, z to the 1 over beta minus 1 dz. Excellent. And we also want to talk about the beta function of p and q being defined as the integral of 0 to 1 dz of z to the p minus 1, 1 minus z to the q minus 1, since this integral is going to evidently be of that form. This integral is just now going to be 1 over beta, integral 0 to 1 dz, z to the 1 over beta minus 1, 1 minus z to the 1 over alpha power. Yep, it certainly does look like this. So we have the minus 1 here already with the beta term. We don't have a minus 1 here, so we have to do a minus 1 plus 1. And this turns out to be 1 over beta times the beta function of 1 over beta and 1 over alpha plus 1. So basically, that's the gist of it. And now we can just go ahead and apply our approximation. We're going to set our approximation equal to this integral with all the constants put back. See what we get. Thanks so much for bearing with me. There are a lot of things to keep track here, but it's really quite straightforward. It's kind of tedious. All right. So, our Bohr-Sommerfeld approximation instructs us to set 2 pi h bar n plus 1/2 equal to what we had earlier with the constants put back in, which I'll just do for you now. 4e to the 1 over alpha plus 1 over beta over d alpha to the 1 over alpha power q 2 over beta times beta times the beta function of 1 over beta, 1 over alpha plus 1. Fantastic. Now, all we have to do is label this En and then solve this expression for En. So we'll be taking the beta over there, we'll be multiplying by, the opposite of this, and finally taking the 1 over alpha plus 1 over beta inverse power to obtain the result that we want. And I'll just go ahead and do this for you. We'll be using the fact that 1 over alpha plus 1 over beta is just alpha beta over alpha plus beta. Not too hard to derive. And this basically tells us right away that E of n is equal to pi h bar beta d alpha to the 1 over alpha q to the 2 over beta over 2 beta function of 1 over beta 1 over alpha plus 1. This is to the alpha beta over alpha plus beta power, and we also have an n plus 1/2 to the same power. Yep. Making sure I did it right. Fantastic. So this looks like a bunch of gibberish. How do we know that this actually means something? Well, let's go ahead and plug in alpha equals beta equals 2. This should result in the same oscillator. I just wanted to note here briefly that we actually were talking about alpha in between 1 and 2. Alpha and beta are strictly between 1 and 2. Talk about why they're defined this way later. We're choosing the maximum case. Okay, so if I do this, then 1 over alpha plus 1 over beta is obviously 1/2 plus 1/2, which is 1, of course. And we're also going to need beta of 1/2 times 1/2 plus 1, which is 3/2, which is just pi over 2. Let's see, anything else that we need? No, that's it. So this actually tells us that En with alpha equals beta equals 2 is just n plus 1/2, that's a 2, times 2 pi h bar d2 to the 1/2 q over 2 beta, function of 1/2, 3/2. Everything that I just wrote down here, we already know what it is. And this is just, finally, n plus 1/2 h bar times some crap 2d2 1/2 times q, which we're going to call the crap omega, n plus 1/2 h bar omega, which you should certainly recognize from elementary quantum mechanics as being the spectrum of the oscillator. So, fantastic. This is cool. But why did we impose these conditions here? Well, we did that because if we impose them, then it's going to be the only energy that is to the first power or linear in n. So this means that the energy levels are equally spaced, which is pretty cool. So for any fractional oscillator besides this one, besides the ordinary harmonic oscillator, they're going to have unequal spacing between them. So you can't just simply add 1/2 h bar omega. And if you enjoyed this, definitely feel free to subscribe. I'll be seeing you next time, okay?